no, gas form. All right, so very similar process. The only thing that's changing are the value of C and temperature. So let's do a little erasing here. So that number is going to change, and those numbers will change. Ooh, almost got it all. So that will change. All right, so specific heat of water. Say it again.
Question 1. Is it 1 calorie per degree Celsius?
It is. However, we're working in joules here, so what is it in joules?
Joules per grams to degrees Celsius. 4.186.
Yep, there we go. 4.186 joules per gram degree Celsius. And then the change in temperature?
100.
Yeah. So 50 times 4.186 times 100. This is the amount of energy it takes in order to get that water up.
$20,930.
20,930.
Joules.
All right. 20,930 joules. All right, now we're going to boil it. Well, we got this stuff over here, so let's see. We'll lasso it. We're now dealing with the heat of vaporization. And what is the heat of vaporization in joules per gram?
$2,500.
2,500. I didn't hear what you said though.
2,500.
Okay. All right. And that math there, 5 times 25 is 125, and then 1, 2, 3. So 125,000 joules, unless I made a Carol's error. I'm sure somebody will point it out at some point. So to boil it, it's going to require, well, that plus that. And so, let's see, again, doing the fancy math, I got 1, 3, 4, wait, no, that's 20, so we'll try that one again. 1, 4, 5, 9, 30 joules. $145,930 joules. So it takes even more energy to boil it than it does to melt it. Which makes some sense. That in order to go from gas to liquid, or sorry, solid to liquid phase, the molecules don't have to be separated that far, but the gas phase, they do have to be separated by much farther distance. And then the last bit, why don't we go ahead and take our 50 grams of now steam and get it up to 20 degrees Celsius. So 50 grams of steam. And I want to get up to 120 degrees Celsius. Getting up to 20 degrees Celsius would not make a whole lot of sense. And at this point, we are dealing with a change in temperature. We're back to this formula here. And so, again, 50 grams times the specific heat of steam, which as I'm sure everyone knows, 2.08 joules per gram degree Celsius. Just like your kindergarten teachers taught you. And then a 20 degrees Celsius temperature change. So 2080. Take them off by a zero there. So 1,000 to, oh no. All right, okay, joules. And then that last bit, 100 degrees Celsius in gas form, up to 120 degrees Celsius in gas form. And I'm making it sound like it's that easy. I mean, usually when I'm boiling water, it turns to steam and it escapes. So you'd have to somehow capture it. 2080 joules. So if there were a problem, let's say on a master set, where you had to take a material and take it from some temperature to another temperature where there's two phase changes, you basically break it up into 3 parts. And you do each part separately.
And then you just add all those joules up.
Yep. So we end up in the end with the total amount of energy is just the sum of those 5 numbers. So it looks like the bulk of the energy was spent in steaming the water, boiling the water.
Makes sense. It's 100 degree
No.
temperature. As opposed to a 10.
Okay, questions before I throw a little bit of reality into this? Not too much. Right?
So when you use the C of V and the C of F, what?
C of V happens when you're going from liquid to gas or gas to liquid. V for vaporization.
Okay.
So if I'm going from liquid to gas, it's a positive number. If I'm going from gas to liquid, I'm losing energy. So it's a negative. And then fusion, the things that are fused together, or fusion of music, which is jazz and rock combined. I mean, fusion brings things together. And so fusion deals with, well, think about freezing is fusion. And it's the same number, just plus or minus going the other direction.
Okay.
Now, we have this nice heat of fusion and heat of vaporization, or latent heat of fusion, latent heat of vaporization. Now, in the, I use C a lot. In some of the videos, I might be using the letter L. L's of F and L's of V. L for latent. So just be aware. Also, we dealt with solid to liquid, liquid to gas, and vice versa. What about solid to gas? What would the heat of, I guess, heat of deposition be? All the numbers that you need are up on the board. Someone want to take a shot at the heat of deposition? Latent heat of deposition. Oh, sorry, latent heat of sublimation. And in whichever, probably joules per gram is going to be the simplest. But if you want to do one of the other ones, go for it.
Do you add them?
Yeah.
So 2,830.
Which one? Which one did you do?
The joules per gram.
And you got what again?
2,830.
I missed the 2,000 part, so that's what was messing me up. Sorry. Joules per gram. plus or minus depending on which way you go. If you're going the if you're sublimating, you're putting energy into it. If you're doing deposition, you're pulling energy out of it. Now, one little bit of reality here is that as we go from 0 degrees Celsius to 100 degrees Celsius, this specific heat actually does change a little bit. Not significantly for what we're doing here, but if you ever were, I don't know what your future careers are, but if you're ever in a situation, just recognize it will change some. Just like with ice, if you went in the other direction, trying to go towards absolute zero, the number does change some. Where are we in time? We got plenty of time here to end today, possibly with the most depressing thought that physics can offer. Any questions before I bring on the depression? Then let's do it. The laws of thermodynamics. I have a thermometer here. And so I've got this glass structure inside, let's assume mercury. As the mercury gets hotter, it expands, and then there's some measurement guide there. So I got a room with a mercury thermometer sitting out front. How many of you have used a mercury thermometer before? Grandparents had it, or your parents had it? Grandparents. Just, I know it's safe, but just the thought of, here's a really highly toxic chemical, but put it in your mouth. There are other places to put it too. That's on the type thermometer. But anyway, so what does a thermometer measure?
Celsius.
Of
Temperature in Celsius. Body temperature we usually measure.
I didn't. The temperature of what? If I have this thermometer right here and it's measuring the temperature of the room,
no,
or sorry, if it's indicating the temperature, what is it? What temperature is it?
If I got right what thermometer is, it's for body temperature.
Oh.
In Celsius.
Okay. All right. So let's do body temperature thermometers. I put it under my tongue. So what is it measuring?
Temperature of your tongue?
No.
The temperature of the glass that's touching the mercury?
Closer.
The temperature of the mercury?
Yes. It's like scales, similar in my mind to scales actually measure normal force and not weight. It's actually measuring the temperature of the mercury. So, but we assume that the mercury is the same temperature as the glass, and that the glass is the same temperature of what's outside of it. Here's that radical, any of you remember what the transitive property is in math?
You can. Wait. Oh gosh, that was like third grade.
Okay, it probably hasn't changed since then, I hope. We're all going to stare at Ty. Does anyone else want to chime in and help them out? You are on your own.
Yeah. I don't know, but as soon as I started, I thought I was like, oh yeah, I know what that is, and then I defined a commutative property, and I went, wait a minute, that's the wrong one.
All right, so this one starts out if A equals B.
Oh yeah, B equals A.
Oh, no, that's the reflexive property. And B equals C.
Oh.
Then A equals C. That's the transitive property of mathematics. The property we're talking about here, this law of thermodynamics, known as the zeroth law of thermodynamics. Basically, it's the transitive property, but I'm going to throw a lot more words into it. If A is in thermal equilibrium with B, and B is in thermal equilibrium with C, then A is in thermal equilibrium with C. So this goes with the mercury is in thermal equilibrium with the glass. In other words, it's finished rising or falling. And the glass is in thermal equilibrium with the room or the body, whatever you're measuring, trying to measure the temperature of. Then A is actually measuring the temperature of whatever you're trying to. It's that assumption. So if you're standing still on a scale in static, not moving, then we pretend that the scale is measuring your weight. So zeroth law, this is not the depressing one. All right. First off, why is it not the first law? Why is it the zeroth law?
It's an assumption that the first law is based off of.
Right, so why was this not the first one and the first one is the second one? Anyone? Why would you bother calling something the zero? Why not the first?
It has to happen for first.
Yeah, but they still did. Why didn't they just make this the first and shifted everything? Made the first one the second, and the second one the third, and the third one the fourth.
So for everything, it has to work for everything. Other laws to work.
No, it is fundamental. So, in respect to what you and Ty were saying, they came up with this after they came up with the first, and they weren't going to bother changing what the first one was called. It got stuck. So they decided, and if they come up with something more fundamental than this, I guess that'll be the negative first. Anyway, zeroth law of thermodynamics. Not earth-shattering. First law we actually discussed on the first day. This is the first law of thermodynamics. And we can make it sound really fancy here. Let's see if I've got the exact wording on the first law, or exact nomenclature of the first law. I just have to keep writing it in terms of ultimately what it is. So let me just pare it down in terms of other things. This is just conservation of energy. This is I got a certain amount of energy in a system. I put energy in, I take energy out, it balances. This is not the depressing one either. Here's the depressing one. The second law of thermodynamics. Yeah, energy conservation is fine, but you will never have a perfect system where energy is actually conserved. In our experiment right here, some of the energy was lost. When I lift a book up off the floor, I can calculate its potential, the increase in potential energy when I put it on the table. But I will burn more energy than it takes to actually put that up here. You will never break even with energy. I guess I can write it as there is always energy lost. And And then we'll throw in the phrase that thermodynamics, where it's understood in thermodynamics, but sometimes they say it, sometimes they don't. Statistically speaking. If you look at a large enough environment, yeah, it is possible. It is possible for all the rain that we see outside right now, it's possible for all of it to freeze right now. Odds are against it, but it is possible. But over the long run, it will just be water on the ground of the roof. Now, this idea that whenever you're trying to put energy into, whenever you're trying to clean up, or whatever you're trying to do, put order into something, you're always going to lose it. That idea that there's always this loss of energy is known as entropy. And that systems have a tendency to increase entropy. In other words, a general randomness. So this is sometimes called the law of entropy. But this idea that all systems, every single system, is eventually going to go to randomness. Think about our world. Given enough time, all of the molecules in our world will sort of drift apart. Eventually, all those molecules, those individual molecules, will eventually break up. In the end, there's just a sea of particles that can't be divided anymore. That's what this is saying. If there is no afterlife, in the end, there is basically a universe full of, well, I guess we'll be floating everywhere too. Another sort of backing behind this is, let's say I've got a particle here cruising along with some mass and some velocity, and I've got another particle here, and they're going to hit. Perfectly elastic collision. Well, what's happening here, even so, without energy loss, we still are going to end up in the same